our next topic is chi-square distribution. Here chi-square distribution, chi value can be represented as chi-square. Like this we can represent. What is the definition of chi-square distribution? Square of standard normal variate. Square of standard normal variate is known as the chi-square distribution. And at here in the chi-square distribution it follows only 1 degrees of freedom. Here it is 1 degrees of freedom. And next, that is z is equal to this this chi-square distribution follows the standard normal variate. That standard normal variate can be represented as z is equal to x minus mu by sigma. This z is treated as or called as standard normal variate. Here chi-square distribution. Now chi-square equal to z square. Nothing but x minus mu by sigma whole square is a chi-square variate with only 1 degrees of freedom. Here we are having only 1 degrees of freedom. If this degrees of freedom is dependent or independent, let us take n samples. Let x1, x2 and so on xn or n independent variates. Here we are taking n independent variates with how many samples are taking, that many of means and variances will exist. So here means are mu1, mu2 and so on mu1 and variances are sigma 1 square, sigma 2 square and so on sigma n square. Then here chi-square value will change. Here we are having n values. So based on this n, chi-square equal to x1 minus mu x1 minus mu by sigma 1 whole square plus x2 minus mu 2 by sigma 2 whole square plus and so on plus xn minus mu n by sigma n whole square. If we add all of this, we can write like this also. Summation I equal to 1 to n. We can replace I in terms of I equal to 1 to n. So chi-square equal to summation I equal to 1 to n xi minus mu I by sigma I whole square. This is our chi-square distribution which follows 1 degrees of freedom. With only 1 degrees of freedom. Now we can write the PDF of chi-square distribution. PDF means probability density function. The probability density function of chi-square distribution. So any distribution can be represented as f of x. Here the distribution is chi-square, so we can write f of chi-square equal to 1 by 2 power n by 2 gamma of n by 2. Here this gamma can be written as this or this. We can write in two ways. So we can write like this gamma 1 by 2 power n by 2 into gamma of n by 2 into e power minus chi-square by 2 chi-square power n by 2 minus 1. This is our PDF of chi-square distribution, and this distribution follows the limits 0 less than or equal to chi-square less than or equal to infinity. This chi-square distribution follows 0 to infinity. Next thing, here we have some properties for chi-square distribution. First property. What is the first property for chi-square distribution? The limits for chi-square distribution are 0 and infinity. So we already learned in the PDF 0 to infinity or the limits for the chi-square distribution. That is our first property. And the next property is the degrees of freedom for chi-square distribution is n. Because here we are taking n independent variates. The degrees of freedom for chi-square distribution is n. And next, third property, the MGF of chi-square distribution is 1 minus 2t whole power minus n by 2. This is our third property. MGF means nothing but moment generating function. And the last one, the the characteristic function of chi-square distribution is 1 minus 2it whole power minus n by 2. These are the properties for chi-square distribution. Next we have to learn additive property of chi-square distribution. Additive property of chi-square distribution. Chi1 square, chi2 square and so on chi-n square or independent chi-square variates with n1, n2 and so on nk degrees of freedom. Here we are taking independent chi-square variates with the degrees of freedom n1, n2 and so on nk. If we add all of those, then we will get chi-square, independent chi-square variates as chi-square variate with n1 plus n2 plus and so on plus nk. That is summation I equal to 1 to n, summation I equal to 1 to k ni. If we replaced I equal to 1, then it is n1. If we replaced I equal to 2, then it is n2. Like that, if we substituted I equal to k, then it is nk. And its applications are, what are the applications means? Where we have to use this chi-square distribution. It is used to test the goodness of it and it is used to test the independence of attributes only. These two only the applications. These two are the important applications. Moment generating function of chi-square distribution. What is the moment generating function of chi-square distribution? Let x be the chi-square variate. We are just estimating that chi-square variate as capital X and the PDF of chi-square distribution is changed as f of x equal to 1 by 2 power n by 2 into gamma of n by 2 into e power negative minus chi-square by 2. But here we take chi-square variate as capital S, x. So we can write it as e power minus x by 2 into chi-square whole power n by 2 minus 1 is our PDF. But here we take in x square, chi-square variate as capital X. So x power n by 2 minus 1 we can write. And the next one, the MGF. We have to find out the MGF. The moment generating function of chi-square variate. Moment generating function can be represented as mx of t, that is equal to expectation of e power tx. Here mx of t is equal to expectation of e power tx. Expectation of e power tx is written as, because this one is in continuous distribution, so we can represent it as integral 0 to infinity. Why I am taking only 0 to infinity means chi-square distribution property. In the first property also, in the first property only, we already told that chi-square distribution limits are 0 and infinity. So this one is a continuous distribution. So I am writing integral 0 to infinity e power tx into f of x dx. This is our formula. Next, f of x can be replaced with this value. Integral 0 to infinity e power tx into f of x means 1 by 2 power n by 2 gamma of n by 2 e power minus x by 2 x power n by 2 minus 1. This is our fx, functional value, into dx. Next, here we are doing integration with respect to x. So, we don't need this constant. 1 by 2 power n by 2 gamma of n by 2. This one is a constant and I am taking it out. Integral 0 to infinity e power tx into e power minus x by 2 into x power n by 2 minus 1 dx. So, here we can change this value. We have to simplify this value. Now, mx of t equal to 1 by 2 power n by 2 gamma of n by 2. Just write the same. Integral 0 to infinity e power tx. As the bases are equal, powers must be added because e power tx minus x by 2 into x power n by 2 minus 1 dx. Now we have to simplify that. 1 by 2 power n by 2 gamma of n by 2 integral 0 to infinity. Take LCM as 2 and take x as a common. I am taking not only x, I am taking negative x. If you are getting confused, first take x, e power x, then t minus 1 by 2, it remains x power n by 2 minus 1 into dx. Same. 1 by 2 power n by 2 gamma of n by 2 into 0 to into integral 0 to infinity. Now I am taking LCM. E power x into 2t minus 1 by 2 into x power n by 2 minus 1 into dx. Next, 1 by 2 power n by 2 into gamma of n by 2 integral 0 to infinity e power x by 2 into 2t minus 1 x power n by 2 minus 1 into dx. I am just separating the two. Next, 1 by 2 power n by 2 into gamma of n by 2 integral 0 to infinity. Now I am taking minus from the power e power minus x by 2 1 minus 2t into x power n by 2 minus 1 dx. Here e power minus x into x power lambda minus 1. E power some negative kx equal to x power lambda minus 1 dx equal to. We had one formula. I am just substituting that formula at here. So this is our formula. Integral 0 to infinity e power minus kx into x power lambda minus 1 dx equal to gamma of lambda by k power lambda. Here this total value 1 minus 2t by 2 is k into x power n by 2 minus 1. In place of lambda we are having n by 2. Now moment generating function mx of t equal to 1 by 2 power n by 2 into gamma of n by 2 into. So our formula is gamma of lambda. Gamma of, here in place of lambda we are having n by 2 by k power lambda. In place of k, we are having 1 minus 2t by 2 k power lambda. Lambda means n by 2. So, in both the numerator and denominator, gamma of n by 2 is existed. So, we can cancel that. 1 by 2 power n by 2 into, we can split this to both 1 minus 2t whole power n by 2 by 2 power n by 2. 1 by a can be written as a because it is the reciprocal of, again the reciprocal of a. So we can write it as a based on this condition. 1 by 2 power n by 2 into, this can be changes. This denominator moves to the numerator. 2 power n by 2 by 1 minus 2t whole power n by 2. In both numerator and denominator having 2 power n by 2. So I am just cancelling. Finally, the moment generating function mx of t is equal to 1 by 1 minus 2t whole power n by 2. So we can write it as 1 minus 2t whole power minus n by 2 because the denominator moving to numerator is negative. This is our moment generating function.